Here's how I mastered DSA. Here's how I mastered trees. Today, we're talking about trees. Trees provide us a way to organize data, to organize files, to organize everything that has a hierarchy, to represent relationship. As you can see here, we have a tree right in front of us, this one. Now, trees are represented by a trunk, they have a root. You plant a seed, and that seed gets grown inwards. It holds the land, the soil between the roots, and then it starts getting all the nutrients from the land, and then it grows upwards. Similarly, the trees that we use in. So, what is a tree? A tree is an abstract data type that is used to represent a tree structure with a set of connected nodes. Well, I took the definition from Wikipedia. So, what we see here is a tree. As you can see that here, these are connected by nodes, and it looks similar to a tree structure. Maybe not. If we invert it, probably yes. And if you can also imagine kind of like something that's grown, not grown upward, but grown downwards here. These nodes are connected by lines which are known as edges. Similar to what we have in, let's say, if it's a triangle, we have edges. Something similar here. So trees, these are known as edges. This one, two, three. So two nodes are connected by edges here. And the main definition for it to be a tree is that everything starts from a root. Everything starts from a root here. So these roots, so now what is the root? Anything, a point from where the tree is starting. Similar to here, which we have, this is the main part, the roots, or this we definitely say this is the root, and this is where it's growing. And similarly, we have this point where everything is growing. This is the root, the topmost here. So when I say about hierarchy, what do I mean by it? Now, hierarchy is something that, because now when I say hierarchy, what do I mean by it? Anything that is. So when I say hierarchy, what do I mean by it? Anything that has an order that needs to be preserved, something similar to how we have positions in a company. You have a CEO, you have a CTO, then there's obviously CEO is mostly the founder also as well. So this is the topmost guy. Then you have CEO, then you have CTO, then you have CFO, and then you have all these things. So this hierarchy can also be represented by a tree, and I'm sure of it. In your life, you must have used a tree data structure. Similarly, what we're doing it in computer science, we use tree to build parsers, and how, if it's a compiler, how the compiler compiles the whole program code hierarchically from top to bottom. That's how it does it. Another thing that you should know is that whenever we are trying to solve any aptitude question or trying to represent a relationship or a family tree, notice the word here, family tree of any renowned individual or any celebrity, a family tree of any renowned celebrity or a politician. So they have, let's say, their name or the great great grandfather, and then they have three kids, or the way we look at the family tree of the Gandhi family. Something similar, kind of like. So the people who are on the up, they have the higher priority, and the lower priority. So the The upper one is known as the parent, and the ones which are connected by via edges, though these are the childs. These are the childs, and this is the parent and this is the child. So if this is B and this is C, so C is the parent of A and A is the child of C. This is what you should be knowing. Next, we are going to be talking about levels in a tree. So this is level 0, this is level. So next move on to another set of terminologies, because how do you master trees and the questions that come up in good product based companies, how do you tackle them? You understand trees. Trees is the basic building block data structure that you need for to understand much complex data structures like graphs and do complex problems like dynamic programming. So trees is because you must have learned about arrays, you have learned about linked lists, and you have learned about stacks, queues, but most of the time we don't come to trees. But we need to understand that there's no specific order that you need for to learn data structures. It's just your need and your ability to learn. And I think starting from a tree is a great way to go on to accomplish and master DSA. Array gives you a lot of thinking because you have just a simple stretch of numbers and you need to perform operations on it. It can be boring because, but it is very important to know that array, if you are able to master 1D and 2D arrays, you are just absolutely amazing, because most of the questions are asked from arrays. But understanding complex data structures like trees gives you the edge. And we're talking about edge here. So now, so in a tree, as I told you, everything starts from the top. Everything starts from the top. So this part here is the level 0. This part here is the level 1, and this part here is the level 2. This whole, I think understanding the whole tree data structure is important because it comes in every technical field or any normal non-technical product-based field that you're trying to get into or trying to understand, whether it's machine learning, AI, ML. Everywhere you see these kinds of knowledge, and everywhere there's a use case for tree. So a tree consists of nodes connected by edges. So as I told you, these are the as I told you, these are the edges, and these are the nodes. So this is the level 0, level 1, and then the level 2. Now you might be saying, you might be thinking, okay, so is that a parent can only have, okay, is that visible? Okay, yeah, that's visible. Okay, so can a parent can only have two children? No, that's not it. A parent can have many children. It's all right. I mean, it can have that, right? It doesn't matter, right? It doesn't matter. What you are saying here is a type of a tree. It's very important to understand that there can be many trees, because if I talk about the file system that I mentioned, so inside of a Linux operating system, you have this root folder, and then you have multiple folders inside of it. You have slash etc, you have slash home, I don't remember exactly, slash mnt. So this is also a kind of a tree here. And there's also a pretty fascinating command in command line that you can try out. It is just the tree. So if you just type it inside of your command line, you might be wrong the command, but if you just type it, you're going to see all of your directories and files inside of like in similar to how a tree works. So represented in a tree structure, you would see them. So let's move forward to the types of tree here. So the types of tree here is a binary tree, a binary search tree, heap, trie, AVL. Now let's get more familiar with these types, and because I think this is very important, and these are special trees basically, because in every use case you require to know, you need to know which tree you are actually using, because you cannot just randomly use a tree. You can get a lot of optimization and a lot of advantages by using a special kind of a tree here. So if you have, what is a binary tree now? A binary tree is a tree where the parent can only have two children. So what you saw here was a binary tree. It was a binary tree. Then this tree is mostly asked in questions that you start when you start getting familiarized with tree question. This is the one that you should be starting out with. Then after you have done that, then a bit advanced but very easy binary search tree, where the left child is less than the parent and the parent is less than the right child. So imagine you have a set of numbers, one, two, not one, two, three. Let's say you have a set of number. Let's say you have 99, you have 8, you have 10, you have 4. These are the four numbers that you have. These four numbers can be represented if with the binary tree, it can be anything. It can be 99, 8, and 10. It can be 4. So there's no any relation between them. But if we follow the relation that is given inside of a binary search tree, there can only be one kind of a tree here. What is that? So it is going to start with 4. Okay, you have to think. You have to think about it. Okay, so the left child is lesser than the parent. Okay, the left child is lesser than the parent. So if that's the case, all of the less elements are going to be the lowermost element here on the left side. This now also, if this is a tree, now this part on the left side and this part on the right side. This is the left subtree and this is the right subtree. So subtree is just a sub part of a tree. It is a part of a tree, right? A part of a tree, right? This is a subtree. This is a left subtree. You would always have a left subtree and a right subtree inside of a binary tree. Yes, that's right. Now, that is why we have called upon here the left child as well as the right child. Now, because all the elements on the left child are less than the parent, so that means that the lowest, the minimum number will be at the bottom in the left child here. Okay, so the least number here, the minimum number here is 4, and then 8 is greater than 4, and 10 will be here, right? Now 99 is greater than the right child, so this here would come 99. This is how a binary search tree would be made if we have just three numbers. If I add a 5 here, now things will change. Now things will change. So what will happen here is that if I show you, you would have now 5 here. So if let's say I place a 5 here, 4 is here, and then 8 is here, 10 is here, and 99 is here. I just randomly placed it at the top. Now if I see here, is it following all the rules here? Let's see. Okay, 4 is less than 5, 5 is less than 8, then 8 is less than 10, 10 is less than 9. Okay, everything seems to be working fine. But can there be another configuration? Can there be another kind of a, so let's check it out. So if I put 9 here, if I put 8 here, and then I put, this is 10, 99. So let's say because let's say, because we need to kind of like balance it out. Because what does balancing mean? There's another concept here that you need to understand is that inside of a tree, you have this is called as the height of a tree. This is known as the height of a tree. It's very easy to understand. And height is always calculated kind of like the total, like you have the top and then you have the bottom. So both things are considered, right? Both things are considered. And that's what's important. Like how much is the distance between these two is just the height, but there's also something known as the depth. And depth can be understood by what we discussed here, which is known as level. Levels are a way to know the depth of a tree. 2, 1, 0. Obviously, the height of this is 3. The levels is 0, 1, 2. Okay. Don't need to like relate both of these things. These are very different. Just height is the whole height of the tree, and depth is how much till the bottom can we reach here. Okay. All right. So also you need to understand is that this can be asked and you should be just knowing about these things that these are also taught in universities that the bottommost node is the leaf node. This is the leaf node. This is obviously the parent but also known as the root because it is the parentest to the great grandfather, right? It's the great grandfather of the whole tree. That's why it's the root. The person who started everything, the clan leader, the great grandmother, the great grandfather. Okay, now these two here, because they are on same levels, these two are siblings. These two are siblings. Ron. So let's say you have John Doe as your parent, and he has two kids. One is Mary, and the second is Ron. So Mary and Ron are siblings, right? And then Ron has their kids, which is Hermione and Harry. So kind of like that. Let's not dive into the movie essentials. So now, as I told you, that we need to be able to balance the whole tree. So how do you know if it's balanced? I mean, it just looks imbalanced, right? You have two here, you have one here. How do we know that? Well, there's another method to know, and because we need to think in terms of computer when we are talking about DSS. So here, if we look at the depth, we look at the depth here. So if I everything is what we need to understand is that everything is relative. So this guy, this node here is a parent, but has nothing, right? So he's a parent of nothing. In computer terms, we call that nothing as null. So he is the parent of null. Okay. Now, null is just the absence of data is known as null. So then 10 is the parent of 99, 8 is the parent of 10. Here, 99 has a depth of like 0. If we just consider it, if we just say, okay, this is the end, then the depth is 0. Okay. If we start from 10, then the depth is actually 1. If we come up here, the depth is now 2. Right. Now, right now, I am saying, okay, this is the total depth. But let's say I just need to calculate the right, because I need, if balancing mean that the right side should also be equal to the left side. Okay. So let's calculate it separately. So the depth for the right subtree is 1, then 2 here. But here the length is, so this is null. Okay. So there's nothing here. Then this is also nothing here, 0. This is 1. So the balancing would turn out to be 2 minus 1 equal to 1. So is this balanced? No, definitely not. To make it balanced, everything should be 0. Everything should be cancelled out, right? So here as well, if I include 5, so 5 should come probably around here, right? Around here. So if I say 5 would come here, 4 would come here, just guessing. So 5 is greater than left child, 8 is greater than 5, 10 is greater than 8, and so on. So is this balanced now? I mean, yes, it is balanced now because if you calculate, we have 2 here and 2 here, 2 minus 2 is 0. It is actually balanced. So guys, this was how you do make a binary search tree. Also, as well as you balancing is done automatically by an algorithm that we'll study later onwards. Now, okay, all right. Let's come to heaps. So what are heaps? So heaps are a data structure that you have used before as well. It gives you the either the maximum value or it gives you the minimum value. And whatever data you insert inside of it, everything gets automatically sorted. It just keeps getting sorted and everything you just get. But this heap that we're talking about, how does it internally work? Well, internally, you use something known as a very familiar data structure now, a tree. You use a tree inside of a heap. How do you use it? Well, we're going to study later onward. Then there are two other trees that you need to know is a trie. Trie is we're going to talk less about these things and much more when we later on study these things. So trie is a tree data structure that is used to hold strings. That is used to hold strings. AVL or red black tree is a data structure which is a self-balancing tree. So whatever we were doing here, balancing all these things, this is done self-balance. So it automatically does this. Okay. Now, why trees? So just like I told you, these are used in file systems, organization charts, searching and storing, databases and indexing. Now, these are some of the practical computer science applications of trees. So, each of these things have one thing in common is that everyone needs a hierarchy. Okay. So, why trees? Whenever you have something which has a hierarchy, then we use trees. Let's look at the implementation of a tree. The implementation of a tree here, as you can see, is that we have a node. What is the what do you know, like how what the tree is built by what? It is built by nodes. Node is the building block of a tree. So first we define a tree data structure, and then we define first we define a node data structure, and then we define the whole tree data structure. Let's discuss implementation of a tree. Implementation of a tree, we have node here. So what is the building block of a tree? A node is the building block of a tree. So let's start with the implementation of node data structure. So here we have this is done in JavaScript, but the essential concept remains the same here. So you have a node here, and in the node is an object. It is created as a class, the class node. Then the constructor we use to initialize the object, which takes on the key, and then the key is equal to whichever key you give, and the left is equal to null, right is equal to null. So the way I told you before is that you have a node, any node you have, and whichever node you have, it is going to have it is the parent of nothing right now. It is the parent of nothing right now, and that nothing is known as null in terms of computer science. So that is why we say this dot left equal to null, this dot right equal to null. So a node is going to have something which is called as the left and the right here. Okay, and the right here. If we have more than that, let's say we have 3 child, then we are going to say we have 3 here. Okay. Now let's go to our tree data structure. So I said class. Now let's move toward class trees. Trees here, we have static print tree where we are printing it, and we have other methods as well where we have basically made a root node, and the left is this, right is this. So we are putting up values using the node data structure. Here, what's happening is that inside of a tree data structure, we have first made a node class. And then when having the values, let's say you got a value, and let's say you got a value and you got the root value as 10 here. Now you're going to say, okay, so if we just initialize it like this, we're just saying it's an integer number, but we don't want that. So instead of doing this, what we're going to do is we're going to say this is our node with the value 10. So the value here, the key here is the value here that we give to the node, and what the value the node will be storing, 10, with null. So this is what we get. Okay. And then you say, okay, now you say, let's say, okay, the root dot left is let's say 8, and then you say root dot right is, yes, you say, let's say 99. Okay, this is going to give me 10, then you have 8, and then you have 99. Now can I say that root dot left is equals to 4? Can I say that? But still we are doing something wrong here, which is not giving the node here. We need to put it inside of brackets and then initialize it as node, then give the value, because these will be accepting a node value, right? We haven't made anything right. One thing that we need to understand is that we can give integer values to them, but we can give them, but because we haven't have any checks here, but remember to give them as node, because otherwise they won't have that functionality of a node of time with left and right child. That is important, that this is the standard, this is the rule of when you are implementing a tree data structure. So you have 8, you have 99, and then you have 4 here. So now if I say root dot left equal to 4, what do we get? Well, we say, well, if we just decode it, root is 10, its left child is 8, and its left child, we're going to say it's 4. That's how we do it. This is still null, and this is still null, this is null. Okay. But what we can do is that we can, instead of doing this again and again, because dot left, dot left, dot left, do you see something? Do you see a pattern here? Yes, we are going to be using loops here. And this is how we actually fill up a tree. And this is the same way we use to traverse a tree. Thank you.